automaton. So please raise your hand if you are familiar with either suffix array or suffix automaton data structure. So who have implemented suffix automaton at least 4 times? Really? You sure? 4 times, 7 times. Okay, nice. So some of you are familiar, some are not. So let's start with the basics. So what is suffix automaton? It is a data structure that holds the information about the string. So let's consider some string. Let's call it S. And for example, let it be abra cadabra. So our goal is to store the information about all substrings of this string. With a substring, I mean a continuous segment of characters of the given string. For instance, ada or braka are substrings, but R, C, D is not. It's a subsequence, but not a substring. So technically, suffix automaton is a directed graph. It's a deterministic finite machine or automaton that accepts all suffixes of the given string. So do you know what is a finite machine or automaton? Well, let me explain a little bit. So you know what is a directed acyclic graph. So a graph with some set of vertices and some directed edges or arcs between them. So acyclic means that there are no cycles in the graph. One vertex of the graph is called the initial one or source of the machine. Let's call it T. And then each directed edge has a character assigned to it. For example, here we have letter A, here letter B, and here letter C. Then some vertices are terminal. For instance, this one will be a terminal vertex. In terms of the machine, these vertices are called states. So what we do, we start from the initial vertex, from the initial state, and then we follow these edges until we reach one of the terminal states. There can be multiple of them. Let's add another edge. Let's assign letter B to it, and let's add another terminal vertex or state here. So we travel along the edges until we reach a terminal state, and while walking this directed graph, we print every time we walk an edge, we print that letter. So if we follow this way, we start from T, then we go here and then go here, we will print A and B. And then when we are in terminal state, we claim that the printed string is accepted by this machine or this automaton. So it's quite simple. Directed acyclic graph with vertices, which are called states, and directed edges, where each edge has a character assigned to it. And then we start from the initial state. We choose any pass, and then when we finish in the terminal state, we claim that the printed string is accepted. So tell me, except of AB, what other strings are accepted by this machine, by this automaton? Exactly. So C and B are also accepted. So because we can follow this pass or this one. So a suffix automaton is the minimal, in terms of the size, automaton which accepts all suffixes, non-empty suffixes of the given string. For example, if we have some string ABA, let's say, so let's construct a suffix automaton which will accept all suffixes of ABA. So tell me, what are all non-empty suffixes of ABA? Of course, A, BA, and ABA. So these are all non-empty suffixes of this string. So now we can try doing the following. Let's have initial state T, and then, of course, we need some edge with letter A assigned to it. Then we need this state to be terminal, and as well as we need letter B coming out from initial state T. And from here we can, for example, we can go here. And we will assign letter A here. And also we need another two. Let me do this way. So this will be B, and this will be A. And we can do this way. So something like this can be constructed for ABA. So again, recap. Suffix automaton is a machine or automaton which accepts all non-empty suffixes of the given string. So it's easy to see that every substring of the string corresponds to some pass that starts from the initial state of vertex and ends somewhere. That is true because, of course, any substring, let's say ada, is a prefix of some suffix. And for a suffix, there is a pass which starts from the initial vertex and ends in the terminal state. And of course, the prefix of that pass will correspond to some substring of the given string. So another property of that acyclic graph, of course, should be that from any vertex, there has to be at least one way to reach a terminal state. So there can be no dangling non-terminal vertices. So from any state, there must be at least one way to reach a terminal state. Okay, so it looks like, so such an automaton really can hold an information about all substrings of the given string. However, a very nice property is that the size of the suffix automaton is linear, which means like the number of states and the number of transition edges, they are linear. And this linear size structure can hold the information about all the substrings, and you have squared n squared number of all substrings. Okay, another pretty obvious thing is that from any state, from any vertex, there can be at most one edge with some particular character. In other words, you cannot have two edges with the same letter on them. Like if you have B here, you cannot have another edge with B on it, right? Now let's, before we discuss how to construct a suffix automaton, we will introduce some notions that will be very helpful in order to get better understanding how we construct and how suffix automaton works.
How can we get the A in the right automaton?
Which one?
BA.
BA?
Yeah.
Oh, in fact, we cannot. So BA, we must do like this, right? Is it correct now? And we need A as well.
Okay.
Yeah, we have it because it's terminal state. Correct.
So after reaching terminal state, we can continue our iteration.
Yeah. So it's in a terminal state. A terminal state only means that like currently printed string is accepted by the machine, but of course you can continue. And another property says that there can be no 0-degree outgoing 0-degree vertex which is not terminal. Okay. Yeah, let's introduce some notions. First of all, we consider end positions. So I'm not sure if these letters are big enough. Just let me know if I need to make them bigger. So end position is a set of positions.
There are some questions in the comments.
Yeah.
Where is BA? What's the other question? Just remember that the color is too bright.
Color is too bright. Okay. Maybe we'll stick to the blue one, which is the darkest. Okay. So if you have some substring of the big string, then end pos is a set of positions where this substring is included into the big string. And by ending position, I mean the last character. For example, if we consider AB, then end pos for AB will be equal to. So let's number the positions of characters in the string starting from 0. So this is 0, 1, 2, 3, and so on. So we have AB here, which means that position 1 will be included in end pos, as well as we have AB here. So this is position 4, 5, 6, 7, 8. Yeah, and that's it. So there are 2 occurrences of AB in abracadabra string. So that's why for AB, end position is a set of 2 positions where we have AB in the big string. Let's say if we have bra, then tell me what will be end pos for bra. 3 and 10. And if we have B, okay, not B, but A, then for A it's 0, 3, 5, 7, and 10. Yeah, and if we have CAD, then for CAD it's only 6. Yeah. Okay, then we will call 2 strings equivalent in terms of ending positions if the set of ending positions is the same for them. For example, if we consider string B, then for string B, the set of ending positions is the same as for AB. And it's 1 and 8. So in these terms, AB and B are equivalent. So this notion allows us to group all substrings into classes of equivalence. So by the set of ending positions. So we state that 2 substrings belongs to the same class of equivalence if the set of ending positions is the same. Then let's see what are the properties of these classes of equivalence. So we say that if 2 strings are in the same class, then 2 different strings are in the same class, then one of them, shorter one, has to be a suffix of longer one. Is it clear? Is it clear? Okay. Yeah, because of course, if they belong to the same class, then there is at least one position where we have both of them ending. So if both of them end in the same position, then of course shorter one is the suffix of longer one. Then for 2 arbitrary strings, if we have 2 strings, let's call them S1 and S2, and let's say that S1 is shorter or the same length and as S2, then there are either two options. The first option is that end pos for S1 and end pos of S2, they have no elements in common. In other words, their intersection is empty set. Or end pos of the longer string is a subset of end pos of the shorter string. So how is that possible? So if the intersection of two sets is not empty, then there is at least one position where both S1 and S2 end in the long string, which means that the shorter one is the suffix of longer one, which means that everywhere where long string ends, short string will end as well, correct? However, for shorter string, the end position set can be wider, can be bigger, can include some other positions, right? Yeah, for example, here we can consider string DAB. For DAB, end pos will be equal to only 8. So, and if we check DAB and just B, then set with one element 8 is a subset of set 1 and 8. Okay. This is the first notion, and the second one is a suffix link. So in order to introduce a suffix link, let's do another observation. So if we have some string, let's say DAB, and end pos for DAB is equal to position 8. Then, if we remove one character from the prefix side, what happens with end position set? It can either remain the same, or it can be larger. It can include more positions because we are removing the letter from the beginning. So actually, this is happening when we remove letter D. We will add position 1 to the set. And then what happens when we remove another letter A? So if we remove letter A, the set and pos will remain the same. Nothing will change. And then when we remove letter B, we have an empty string, which is like everywhere. The end pos will become wider and will include all the locations. So this observation leads us to the property that if we check all the elements in the class, in some class of equivalence, then there will be the longest string, the longest representative of that equivalence class. Let's call it longest of some class of equivalence, and all other elements in the class C will be suffixes of this longest string. In our example, we have AB and B in the same class of equivalence. So AB is the longest string here in this class. And all others, in our case, just string B, are suffixes of the longest string. Moreover, there is a shortest string in class C. In all the strings of all lengths from this length to this length will be included in the class. For instance, if the size of longest string is 7 and the size of the shortest one is 4, then strings of lengths 4, 5, 6, and 7 all are included in that class. And only these strings are here. Which means that actually we can represent a class of equivalence with just a few properties. First of all, the longest string which represents the class, and then the shortest string of that class. So as soon as we know the longest one and the shortest one, then we are good. We know that all others are simply suffixes of longest. And lengths of all the elements are in the range between the size of shortest string and the size of longest one. So now this is the process we have just considered. Every time, if we take the longest string, and if we remove one letter, one character from the prefix side, then we'll move towards the shortest string. And then when we have the shortest string of the class of equivalence, here that's string B. When we remove another letter from the prefix side, we will get some shorter string which belongs to some other class of equivalence. So this actually is an important information, and we would like to know where will we get if we remove one letter from the shortest string in our class of equivalence. And let's do this connection, and let's call this connection a suffix link. Let's connect two classes of equivalence with the suffix link, and that suffix link means that we will make the end position set wider, and we will move from this class of equivalence to the wider one by removing exactly one letter from the left, from the shortest string in this class of equivalence. In other words, if we have a suffix link, let's call it just link, of some class of equivalence C, then the longest string of the class where our link points to, the size of this longest string is actually equal to the size of the shortest string of our class C minus 1. So in our example, we had a class of equivalence with strings of lengths 4, 5, 6, and 7. And then there is another class of equivalence which ends with length 3. And there will be a suffix link from here to here. Okay, then if we consider all suffix links for all classes of equivalence, we will get a rooted tree. So the root of our tree will be a special initial state of our automaton. So we have our state T, and then we have our classes of equivalence. And suffix links. If we use our end position sets, and if we build another tree by the property of one set including another one, so from our previous observations, we know that two classes of equivalence, they either do not intersect or one of them contains another one. So if we use this property and if we put a directed edge from a set which is contained in the bigger set, then we will get exactly the same rooted tree as the one with suffix links. So let's recap everything before continuing with the actual algorithm of how to construct a suffix tree. So for we consider all the substrings of the initial string S. We group this substrings by ending positions, by the set of ending positions. And each such group is described by simply a collection of positions where a substring, which is included in the initial string, ends. Then, for each such group or class of equivalence, we create a vertex in the tree, and we add a link or so-called suffix link from a state or a class of equivalence to some other wider state. Every group of equivalence, every vertex contains a continuous set of substrings, from the shortest one to the longest one, where all the substrings are suffixes of the longest one. And all substrings from the given range are included into that class of equivalence. For the root vertex or class of equivalence or state T, we define a suffix link as unknown, or we can actually include some special set of positions where we have all the positions from 0 to length -1, and we will include -1 as a position before the first letter. Okay, so it turns out that the number of classes of equivalence, the number of these groups, is actually linear. And as well as the number of transitions. So here we only see suffix lengths. However, we also have transitions between the states, and every transition corresponds to an edge in a machine we described before. So every transition has a character assigned to it. So it turns out that the number of states, groups, or classes of equivalence, as well as the number of transitions or directed edges, is linear. So we will now describe how to construct a suffix tree given the input string S. And from this construction, we will see that the number of vertices is linear, and the other properties, including the statement that the automaton will get at the end of the algorithm is minimal possible, is out of the scope of our lecture. However, you can easily get more additional information over the internet. So let's construct a suffix automaton in the online manner. Yes. So the question is, what is the difference between these two different types of arrows or edges I draw here? So these edges are suffix links. So suffix links, they simply say that for example, if you have DAB, well, class of equivalence which contains DAB, and there is a suffix link which leads to AB. So it says what is the class of equivalence which contains the longest string, the longest suffix of DAB. So that's the suffix link. And another type of edges are transitions. So transitions are edges of the deterministic finite machine, which means the letters you print when you traverse the automaton. So, like, if you start from here, let's say A, let me put it this way. So if you have DAB, there will be a class of equivalence which contains DAB and R. So there is this type of transition with letter R on it. It means that if we follow this transition, we have to print letter R, and we have to reach some class of equivalence which contains strings from here plus letter R. So these are transitions, and these are suffix links. So suffix links are just the suffix links. They do not belong to the finite machine. They are not used to generate a printed string. The suffix links are just some helpful information we will use in order to make the best use of suffix automaton.
Question.
Yeah.
The number of edges is linear.
Well, like I said, by the way, it's important thing that here we assume that the size of the alphabet is a constant. So all these things, when I say it's linear, it means that it can be the length of the string multiplied by the size of the alphabet, and it's still linear. If the size of the alphabet is not linear, and we have to take it into account as well, then we'll have a different complexity. It has to be multiplied by a log size of the alphabet. Again, like I said, after the description of the algorithms, we will see why the number of vertices is linear, and we will have an upper bound for that. And we will also prove that the number of these transitions, suffix links are pretty clear. The number of suffix links is the same as the number of vertices. And for these transitions, we'll prove that the number of these transitions is at most 3 times the length of the string. Yeah, but that will be discussed after we construct the suffix automaton. Okay, so let's build the suffix automaton in the online manner, which means that we will add letter by letter. So we will start from empty string S, and then we will append A, B, R, A, C, and so on. So we will modify our suffix automaton in online mode. Okay, so initially, our string is empty, and we have just one vertex in the suffix automaton, which is initial state t. So now we will describe the process how to add a letter from the right to the current string. So we will denote that letter with C. So we will be appending character C from the right. So now let's assume we have some suffix automaton already built for string S. So these are suffix links, and these are some transitions. So let's consider the state, the vertex, which corresponds to string S. In other words, we need that vertex, which is a class of equivalence, which contains the whole string S. Let's call this state lost. So now what happens? We enlarge our string by appending character C. So in other words, what we intend to do is to add a transition with letter C from the last state to some new state. So let's do it. We will add a new vertex, a new class of equivalence. Let's call it current. And then let's add a transition, an edge, with letter C on it from last to current. However, it might happen that a transition for, okay, so there is no transition from the last, because last corresponds to the whole string S, and there can be no other transitions. However, this is not everything. We also need to consider those states that are reachable from the last by suffix links. So why is that? Because last, so if we have some string S, then last corresponds to some interval of lengths. Let's say, so this is the longest for the last, and let's say this is the shortest. And we are appending C here from the right. So this state corresponds to all suffixes of S from longest to shortest. So all of them are included here. So and when we append a character C, then we travel this edge, and we are in the current state right now. However, if we move up the one step via suffix link, then we'll get to some other interval, which contains some smaller suffixes of string S. And since we are appending character C from the right, so this also has to be resolved by adding a transition with character C on it. So what we do, we move up via suffix links until we get a collision. So what is a collision? That's the case when some vertex, some class of equivalence, already contains a transition with letter C on it. It could actually happen that we reach an initial state and we find no vertex on our path with C letter transition coming out of it. So this will be the case number one. So the case number one, no C letter transition state. So on our way from the last to the root of the tree, there was no C letter transition state. So in that case, we simply add C character transition from each of them to the new current state. Otherwise, yeah, and in that case, we have to add a suffix link from our new vertex, and it will be connecting us with the root of the tree. Otherwise, option number two, we encounter a state where there is, let's write it down, where there is a transition with letter C on it to some different state. So let's call this state P, and let's call this state Q. So we have reached state P, and for state P, there is already a transition with letter C on it. So that means that by definition, we cannot add another transition with letter C on it. So we have to somehow use this existing transition. Then there are two options. Option 2A says that if the lengths of the longest string in the state Q is equal to the length of the longest string in state P plus 1 or not. So in case 2a, the longest substring in Q is one letter longer than the longest string in state P. So when we have a transition from P to Q, how these two values decide of longest, how can they relate? For every substring in P, we add a letter C, and there must be this substring plus letter C in equivalence class Q. But of course, it can be wider. Like there can be some other incoming transitions to state Q. So which means that the size of longest string in state Q is greater than or equal to the size of the longest string in state P plus 1. So it is at least the size of the longest string in P plus 1 or greater than. So do you understand why?
Because you have one.
Yeah, because we have to add one letter, but do you understand why it can be bigger than?
Because we can have other transitions.
Other transitions, other incoming transitions. Exactly. So, okay, so case 2a is when they are equal. I mean, longest, the size of longest and the size of longest plus 1. And case 2b, when it's greater than. Is greater than longest P plus 1. Okay. So if they are equal, so what can we do? Like, it's exactly what we need. The equivalence class, where the size of the longest representative is exactly the size of the longest P plus 1. That's what we need. And the last thing that we have to do is to assign a suffix link. So tell me, how should I assign the suffix link in case 2a? So if we are here in current, so the suffix link is currently missing. And let's say that we have, so this is our state P, and this is our transition to state Q with letter C on it. So just make a guess.
Could you please explain with some real examples?
With real examples. So I'm afraid we simply don't have time for it, because it's like we actually have to start a contest in 10 minutes, but we'll postpone it a little bit. So I'll finish with this, and then if we have time, but I'm afraid we won't. Okay, so just make a guess. How to assign a suffix link into A? What are the options? So we have either P or Q. Let's toss a coin. Let's vote. Q. Okay, Q. Why Q? Because not P. That makes sense. So let's assign a suffix link from the current to Q because it's not P. And since P is somewhat similar to NP, hard problems, then let's just not mess with P. Let's stick with Q. So yeah, as we have a letter C added here, then from the current state, the next one, which will be wider, which has been existing before it, is definitely a class of equivalence which corresponds to Q, and the size of its longest representative must be exactly the size of longest P plus 1. So, and that's the case. That's what we have here. However, we have the case 2b, where a state Q has its longest representative too long. We need it shorter. So in this case, we have no other option than split a state Q into two states, into two vertices. So let's do it. So let's consider option 2b. For 2b, what we do, alongside state Q, we create state Q. Let's let it be Q1, and this will be Q2. And by splitting, I mean copying or cloning the state, which means that we, for all the transitions coming out of Q, and for the suffix link coming out of Q, we copy the same information here. So it contains basically everything the same that Q1 has. Except we now claim that the size of the longest representative for Q2 has to be exactly the size of the longest representative of P plus 1. So which means if we have this picture where so this is long for Q1, and this is short for Q1. Okay, so that's what used to be before, and now in the middle we cut this class of equivalence with the long P plus 1. So this keeps to be Q1, and this becomes Q2. So we split the state into two with the length of the longest representative equal to longest P plus 1. Okay, so which means that now we have to change the suffix link for Q1, of course, because now Q1 must point to Q2, because Q2 is shorter, which means that the ending position is wider.
Can you repeat how do we split Q?
Okay, so how do we split Q? We copy the state. We copy all the information of transitions with characters. So all these outgoing transitions with characters, we simply copy them, and we copy the same suffix link. So we have Q1, Q2. However, for Q1, we keep the same longest representative, and for Q2, we make the longest representative to be of the size longest P plus 1.
So we just cut some brackets, and the longest changes, but short doesn't.
Yeah, for Q1, shortest changes. So let me Let me put it somewhere here. Okay, so it used to be longest and shortest for Q1. Yeah, and here in the middle, that's what we have, longest P plus 1. So now we keep the longest for Q1, but we shift shortest. And we create, we create Q2 where longest 2 is set at this value, and we keep the same shortest as it used to be for Q2. So you can actually observe a class of equivalence as a collection of continuous substrings. So we have like shortest substring and longest substring, and everything in the middle is included. So what we do, we simply cut here. Cut by this value that we actually need for the suffix link of the current vertex. Yeah, so after the split, that's Q1, and that's Q2. Okay, and since Q1 has a longer substrings, every time when we make it shorter, we'll reach its shortest representative, and then when we drop another letter, we'll fall into Q2. So that's why we have to assign a suffix link from Q1 to Q2. As well as for the current vertex, we have to do the same, as that was the desired value. We'll assign a suffix link for the current vertex to be Q2. Unfortunately, that's not the end, because this case is a bit kind of complicated. We have to do some extra transition changes, which means that starting from vertex P, we move up using suffix links, and until okay, let me use some space here. So that's P, then suffix link P2, P3. So we move up with suffix links, and until there is a transition with letter C on it to the state Q1, we have reassign or change it, and we have to direct it. Instead of this, we have to make it to Q2. And the same for here, and here, and so on, until such a transition exists. So if we move up, and if at, let's say, this step, there is no transition with letter C on it, which leads to the state Q1. Q1 is the same as former Q state. Yeah, if there is no such a transition, then we stop, we break. Okay, so we have 1 minute left. Let's wrap it up. So it's not very trivial, and I would say kind of complex algorithm or data structure. However, if you spend more time with it, and if you just let it a chance to reside in your brain, then you will find this data structure very, very useful and very powerful for solving problems related to strings, substrings, and so on. We'll later address what types of problems can be solved with suffix automaton. But first, let's see. This is almost the end. We now know how to construct a suffix automaton, but we have no idea what states should be terminal. Recall that a suffix automaton should accept all the suffixes of the initial string. Then, if you make friends with this suffix links, then it will be almost obvious for you that it's very easy to mark terminal states. If the whole string S is constructed, then by the way, at the end of that iteration, we of course reassign the last state, the last vertex, to the current. So let's consider the vertex which corresponds to the whole string S. Of course, that state must be terminal, because string S is inside this class of equivalence. So we mark the last state as terminal. Now, like we had the picture here. So the last state contains some range of suffixes, of string S, but not all of them. So this part here is like the beginning of the suffix. So in order to include other suffixes, what we have to do? We have to move using suffix links, of course. So from the last state, we move up via a suffix link, and then we mark. So if we go here, then we have to mark this as a terminal, and then we move up and mark all the states on our way from last to the root as terminal states. And in this manner, we will actually cover all suffixes of the initial string. As like by moving up the suffix link, we will simply traverse all the ranges of suffixes of the initial string S. Okay. The next observation is the number of states. So we already mentioned that the number of states, the number of classes of equivalence, is linear. So it's easy to see from the construction algorithm that the total number of vertices is linear. Why? Because at every time when we append a letter to the right of the string, we add one or two vertices, one or two states. So it's easy to see that initially we have one, and then at every step, +1 or +2. So the total number of states or vertices is at most 2 times n. Yeah, since at the very first step, there will be exactly one vertex added. So that's why up to 2 times n, where n is the length of the string S. Like I said, the proof of the fact that the algorithm actually builds the minimal possible deterministic finite machine or automaton, it falls out of the scope of our language. Finally, let's address what problems can be solved by this data structure. First of all, very simple. You're given a string and another collection of search terms, and your task is to find all occurrences of search terms in the long string. So, of course, this problem can be solved with some other techniques, some other algorithms, but definitely you can apply suffix automaton in order to find short string within a long string. So who can tell me how should we use suffix automaton in order to search a string into another string? First, step number one, let's build suffix automaton. That was unexpected. So what is step number two? So I'll introduce some other. So let S be a long string and T be a short string. So T is a search term. So how to check whether T is in S?
So we can run just by automaton.
Use KMP. Again.
We can run just by automaton by string S.
Yeah, exactly. Thank you. Unfortunately, I don't see who is talking, but you're so right. Yeah, so we can simply iterate over characters of T and use our suffix automaton. And if at any point we can, there is no transition for the current character, then we fail. Otherwise, we are good. And note that for every substring of string S, there is a pass from the root of the suffix automaton to some vertex, not necessarily the terminal one. Okay, so another problem we can solve with suffix automaton is, for example, if you have a string S and your task is to count how many different distinct substrings are there in string S. So that is also a problem which can be easily solved with suffix automaton. Maxim, could you tell us how to apply suffix automaton to this problem? Not really. Not today. Not really. Okay, Bogdan.
You can populate also some things like how many we can keep some other thing state of some other.
Yeah, for example, what?
Like, for example, number of strings to which corresponds the current state. I don't know.
So again, so like I said, for each substring of S, there is a pass in suffix automaton.
Okay, we can do dynamic programming.
You can do a dynamic programming. Absolutely. So you can do a dynamic programming because that's a bijection. So for each substring of S, there is a pass in suffix automaton which starts from the root and ends somewhere. And vice versa, for each pass in a suffix automaton, which starts in the root and ends somewhere, there is a corresponding substring. So it's one-to-one. That's why all we have to do is just to count the number of paths in suffix automaton, which starts from the root. And you can use, since our automaton is a cyclic graph, then for a cyclic graph, you can apply dynamic programming in order to calculate whatever. Great. Then another problem. So you're given a string S, and your task is to find the shortest string which is not a substring of S. Maybe you have already solved such kind of a problem. Again, so you have a string S, and your task is to find the shortest string T, which is not a substring of S. So imagine we have an alphabet,
And if there are many of them?
Any lexicographical is the smallest one. So if you have just 2 letters in your alphabet, and if S is equal to A, B, A, then what will be the shortest string which is not a substring of S? Definitely BB, correct? Yeah, but if we have something like this here, then we will have to check something else. But in general case, can you solve this problem with suffix automaton, or maybe with some other algorithms? So again, note that every substring of S is the path in suffix automaton, which starts from the root. So if at any point, so there is like a missing transition, so you can use that missing. For example, there is a root T. So if there is a transition
Do another dynamic program.
to another dynamic program,
Which means like value of state means the length of how many edges must we pass to enter a vertex, so where there is no edge. Is some.
yeah, absolutely. So
And
anyone who understood? Great. So you're a team. You must be a team, right? Okay. So again, if you have the initial state, and if some transition is missing, let's say we have no transition with letter B on it, then of course we can simply use letter B. And since there is no transition on letter B, then B is not a substring of S, right? So, but if there is a transition on B, then we can either move here or here. But then, like in these 2 vertices, we are interested in the one which generates a smaller result. So that's what Bogdan mentions. You simply use dynamic programming. Okay, so and the last one, we have multiple strings. Let's make it a bit more complicated. We have multiple strings, and your task is to find the longest common substring. So you have to find a substring which a substring of all of them, which is the longest. Something like that. So how to solve this one?
Iterating simultaneously in all the suffix structure and use the same dynamic program.
Well, not really. How could you know which path to take? Well, you will have, like, if you build suffix automata for all of them, then they will be different. And like for some of them you have transition, for some you don't, and yeah, it's. But let me give you a hint. This one can be solved with suffix automaton. Does it help? Yeah, so you're more eager to solve it. And as you might already guess, you can use dynamic programming here as well. And as you see from those examples, a combination of suffix automaton plus dynamic programming built on top of the acyclic graph is a very powerful combination, and a lot of quite different, difficult text processing problems are solved with this combination. Okay, so let me leave you this one for a home task. Unfortunately, this was a quite short lecture because we had a limited time, and the topic is very wide. You had a right query to use some example in order to get better understanding of the topic, but unfortunately, since we are limited in time, there was no like real examples, no implementation on the whiteboard. However, we tried to discuss general ideas behind suffix automaton and the problems which can be solved with it, along with the most important properties and notions like ending position sets and suffix lengths. So I recommend you to spend much more time and discover a lot of information available right now in the internet related to suffix automaton and related problems. Besides, there are numerous of problems which are solvable with this data structure. So that's everything. If you have any final questions, feel free to ask. Then we'll proceed with the contest. The contest, let's try to start at 11. So make sure to register your team for the contest, and don't forget about the clarification section at the contest page. Okay, so good luck, and after the contest we'll have a lunch, I guess, and after the lunch we'll get somewhere for problem analysis and result announcement. So thank you for joining us today. Yeah, it's still pending. We'll confirm it just before the contest starts.